Hey guys, welcome to my video on UHS MDCAT chemistry for A-level students, and we'll be doing questions from the organic topic. And the purpose of this video is to familiarize A-level students with the FSC coursework. Let's get to it. There are a total of 58 out of 220 questions that will be coming from the chemistry part of the FSC coursebook. Almost 30 of these will be coming from the part 2 book, and that is the one I would suggest you put the more effort in, because not only is it easier, it also holds more weightage. So question number 1. The IUPAC name of the following compound is. Well, number 1, let's see. How many carbons does this compound have? 1, 2, 3, 4, 5, 6, and 7. And how many double bonds? 3 of them. And we start naming from the end that is closest to one of these double bonds. So this one. We have a double bond at carbon 1, at carbon 3, and at carbon 5. So it's 1, 3, 5 heptatriene. Hepta is representative of the fact that we have 7 carbons. Ene is representative of the existence of the double bonds, and tri shows that we have 3 of them, whereas 1, 3, 5 shows the locations. This is easy peasy for A-level students, not much of a problem. So which of the following is not an electrophile? An electrophile is a electron deficient species. AlCl3 is indeed electron deficient. Its octet is not complete. This appears to be CH3. I'm not all that clear because it's not visible, but it's probably this way. And in both cases, these are electron deficient species. This is an alkyl group, whereas this is an acyl group. Over here we have SO3, and SO3 is not what you would call electrophilic because it has this configuration. Though it is indeed used as an electrophile in some cases, you would not consider it to be an electrophile as such, even though you can use it in electrophilic substitution. But if this were negative, that would suggest that it is not an electrophile. But I would say skip this question because it's not really all that clear. So butyl alcohol shows number of possible isomers. Butyl alcohol is basically 4-carbon alcohol. So we can have for a straight chain we can have a primary and we can have a secondary. We can also have a tertiary configuration, or we may have it over here. So that makes a total of 4 possibilities. So it can be over here, or it can be over here. It may be in this formation, it could be over here, or it could be over here. And if it's over here, over here, over here, it will have the same it will be same molecule because these are equivalent compared to the C. So there are a total of 4 possible isomers of butyl alcohol. That includes both position isomers as well as chain isomers. And for now we're just considering the structural isomers and not the stereoisomers. So alkenes are normally, would you consider them weakly polar, strongly polar, polar or non-polar? This is a bit of a question because while they aren't exactly polar, because the electronegativity difference between the carbon and the hydrogen is negative, we do in fact have this electrophilic quotient. So perhaps calling them weakly polar would be a good safe point. Nonetheless, let's see what the book has to say about it. There are probably some hints, if not being written all together. And you'll find the alkenes on page 136 of the second year book. The alkene portion will start from page number 148. They haven't termed them as such anyway, unfortunately, but in the properties they've said that unlike alkanes, they show weakly polar properties because of sp2 hybridization. Again, I would suggest you take a look at the physical properties from where they're written, because while it's not written in the syllabus, they often come up. Let's read more. They also have this characteristic smell, and they burn with luminous flames. It means that they have a particular flame color. They're water insoluble but alcohol soluble. The first three members are gases at room temperature, whereas from C5 to C15 they are liquids, and the higher members are solids. I think this is something worth writing down. That's C1 to C3. We're talking about the alkenes, C1 to C3 gases. C5 to C15 are liquids. These are the important stuff to remember. They have characteristic smell that is also of some importance. The luminous one is particularly important. So let's move onwards. In cis-trans isomerism, the cis form shows all of the following properties except polar molecule. Now cis means on the same side, so it's likely to be polar. Unsymmetrical. That depends on what you're talking about, but generally they would be unsymmetrical. If you're talking about, like if the double bond is cut across the middle, it's likely to be unsymmetrical. Low boiling point. And this over here means dipole moment. So they're saying that in the cis form, the dipole moment is not equal to 0. You would be right. Cis form means they are on the same sides. So like this, for example, and this. So in the cis form, it's unlikely that it would completely be cancelled out. So this is correct. Are they polar molecules? That is a good question, because it's really dependent on what's on what side. Are they unsymmetrical? Well, yes, they are indeed unsymmetrical. Do they have low boiling point? Well, that is not necessary. That is something that is dependent on the side chains that are attached. They are likely to be polar because of the lack of symmetry. I would say the low boiling point might be the incorrect one. This one should be subject to some amount of research. The problem with these questions and the ones that come up with the UHS is I find them somewhat non-standard compared to the A-level ones. It's like sometimes they put up questions without any kind of thought involved. It's a bit annoying occasionally. Phenanthrene is a condensed aromatic compound. So the number of rings in this compound are, so we have anthracene, and anthracene is a fused molecule, and said fused molecule is said to have, I think it's like this or something, and actually it's more like fused in this sort of manner. But phenanthrene is something perhaps a bit different. So they're saying it's a condensed aromatic compound. So what are the number of rings in this compound? If it's the same as anthracene, it should have 3. Let's take a look at the aromatic compounds topic. Maybe we missed some formula at the edge of the page. Yep, they do that. Will be some small microscopic tidbit at one end, and next thing you know, it's in the papers. Freaky, to be honest. So we're there, and yes, phenanthrene is indeed over there, and phenanthrene is pretty similar to anthracene, but not quite. But I was right on the mark, it has 3. So the thing, if they ask you if there is any difference between anthracene and phenanthrene, you would say that no, there isn't any difference in terms of the formula or in terms of the molecular mass, but there is a difference in terms of the structure, so they can be said to be isomers of sort. And the name is surprisingly similar, so people often get a bit confused. This is one of the rings, and attached is the second one. Now this was anthracene, the third one would be like this, just like these, but if it's anthracene, then it's going to be like this. So that is the special thing about phenanthrene. So you have to be really careful, because in terms of common names and in terms of the structure of strange sounding compounds that can be found literally anywhere, sadly, and you need to be really careful that you don't confuse the structure of anthracene with that of phenanthrene, because they're indeed freakishly similar. So some are really easy, but if they ask you what toluene is, phenol is, aniline is, benzoic acid, benzaldehyde, you should be clear on what they are. Biphenyl is something they can give as well, and you'll be like, phenyl, what is that? It's exactly what you think it is. It's 2 benzene, but they're not fused. It's a non-fused compound. It's like this. So they're basically 2 benzenes, but they're not fused. They're attached, but they're not fused. You need to make the distinction between the various different types of compounds. suggest you take out your books right now and see if there is any such compound that you may have missed out, because when you get the inspiration, you remember to do something, it's better to do it at that moment, because oftentimes we end up forgetting up. So what about diphenylmethane? That is another interesting molecule. Diphenylmethane, like biphenyl, is composed of two phenyl portions, and they are indeed attached together without being fused, except there's this intermediate, this joining molecule, you can say. It's like this. In addition to this, any other interesting molecule? Naphthalene is easy, so is benzene. You ought to know what O, M, and P mean. Do you know what xylene is? Xylene is basically like toluene, but xylene is when it contains two CH3 portions. So we have one CH3 on a benzene, and the other one is directly opposite it, meaning on the 4 position relative to it, meaning the para one, it will be p-xylene. Or if it's on the one that is adjacent to it, that would make it orthoxylene. Or if it was, say, on the third compared to it, it will be M-xylene. And there were some other molecules of strange origin that were in the macromolecules topic, so I would suggest to take a look at these. This is phenananthrene. God, I'm bad at this. And this over here is biphenyl, and it's important that you remember it's called biphenyl. And over here we have diphenylmethane, I believe that is what it's called. Because of this portion, we have two phenyl and we have this methane. And in addition to this, if we have an arrangement like this one, we have CH3 over here, we have a CH3 over here. So this one is the first one, we're assuming this was the first one, so we are sort of like ignoring its marking. But this one, the other one, is 4th position relative to it, and we know the 4th position is often referred to as the I believe it's called the, if I'm not mistaken, it will be called the para position. Ortho is 2, para is 4, so this will be p-xylene. However, if this was the first one and the second one was over here, so this would be the 2 position called ortho, so it will be O-xylene. And if it happens to be on the 3rd position, and we know we usually refer to the 3rd as the meta, it would be M-xylene. And something to remember is the fact that the presence of certain functional groups gives the ring certain names, and so we retain said names if there is another substituent, and we make that special name the base. And that's a bit confusing. Don't worry, I will give you an example right over here. It's like this. So if we have this sort of a molecule, we have a benzene portion, and over here we have this attachment, which is SO3H, so it's called benzene sulfonic acid, right? Or if we have say an OH, it's called phenol. And if it's like this, it's called toluene. And if it's like this, we call this aniline, right? So if there was this sort of a molecule that we had an NH2 over here, what would we call it? Well, both the presence of OH and NH2 give it this special sort of name, but you should know that OH has the priority in naming. So name of the ring relative to OH is retained, that is the phenol is retained, and we make this a substituent. So this molecule will become 4-aminophenol. If you have a molecule like this one, call it chlorobenzenes, there isn't any specific name. So if it's over here, even though Cl and CH3 have basically the same amount of priority, but because this doesn't give any sort of a special name, we will retain the toluene name. We'll call this 4-chlorotoluene. And as I said, this is called benzene sulfonic acid. So if we have a Cl over here, as I previously mentioned, Cl doesn't give any sort of a special name, it becomes benzene sulfonic acid. So these are the important ones, but there are a few others that are particularly important. In the macromolecules, especially in the topic for macromolecules especially, they gave a few that were really confusing, and to me pretty upsetting because I had a hard time remembering them. There was one such molecule that was something like this. And this was oh, I'm sorry, actually drew this the wrong way around. It was like this. Except instead of there being an attachment, there was a carbon in the middle that was part of like an isopropane or something, and there were OH attachments over here, and I think the name was diphenylol propane, and this was a really strange molecule for me. I had never encountered such a molecule before. And there was another one. And I think it was epichlorohydrin. And these two were actually monomers for this compound. this condensation polymer, epoxy resin. That was really important, especially in weather-resistant paints. But the reason I'm telling you this right now is because of their strange names, because they often bring up the common names and they start talking about something you'd probably know if you knew what they were talking about, but because you were unfamiliar with those names, you mess up and you lose easy marks. Well, I wouldn't call them that easy, but pretty. So yes, let me confirm. This is indeed epichlorohydrin, and this over here is diphenyl propane. And from when we condense these two monomers, we get epoxy resin by the condensation of epichlorohydrin and diphenyl propane. And you should note that the resulting epoxy resin are fundamentally polyethers, something they can ask you. And what is the major use of epoxy resins? It is in coating materials to give toughness, flexibility, adhesiveness, and chemical resistance. So oftentimes industrial materials or thermal power stations or packing material are coated with them, even dams, bridges, and floors. I'll repeat this because these are one of the more obscure parts of the syllabus, the ones we are completely unaware of as A-level students. So I'll repeat these because they ask functions very well. Often we don't usually get these sort of questions that are so theoretical, but they do come up in FSC. So they quote materials to give, and I'm talking about not these monomers but their product, which is epoxy resin. I can't emphasize this enough. And it gives, number one, toughness. So because of this quote, the materials are likely to be more tougher. Number two, flexibility. And the third point is adhesiveness, the ability to be glued together. And lastly, chemical resistance. So now these are the properties that they give, but where do we use these? What sort of substance do we end up coating with these? They've given a lot of like industrial materials, like trains and stuff, or stuff that might actually be used as a raw to make other products. Thermal power stations, because there's a lot of fuel being burned, a lot of chemicals being given off, and the machinery needs to be protected. And packing material, in addition, dams, bridges, and floors may also be coated as such. Anyways, let's move onwards. The type of orbital hybridization of carbon and ethane is definitely sp3. And what is the application of cracking? To increase the yield of petrol to produce petrochemical, both A and B, neither A and B. It's actually to produce gasoline from the cracking of heavier fractions. So we'd go with neither A nor B because petrol is pretty heavy, one of the more heavier components. Just to be sure, let's go over this topic, and the cracking topic is found in Fundamental Principles of Organic Chemistry, page 118. And this topic isn't given a lot of detail. They've included cracking of petroleum, not the petroleum topic itself, but let's go with that. Mineral oil is called petroleum when it is in the refined form. So mineral oil is the raw form. When we refine it to an extent, it's called petroleum. It is thought to have been formed by slow chemical and biochemical decomposition of the remains of organic matter found between sedimentary rocks. When extracted from rocks, it appears like a liquid of blackish color known as crude oil and is refined to get different petroleum fractions at present. We have 4 oil refineries, and the crude petroleum is separated by fractional distillation into a number of fractions, each corresponding to a particular boiling point range. So we get natural gas, we get petroleum and ether, we get ligroin or naphtha, we get gasoline, we get kerosene, we get gas oil, lubricating oils and greases, paraffin, asphalt, or petroleum coke. And if you look it up, they're telling that the main sort of like job of petroleum is to get gasoline, which is only about 20% of the petroleum yield, and the composition of the products depends on the conditions, and catalytic cracking is the one we use to get the best quality gasoline. Thermal cracking and steam cracking is used to get unsaturated hydrocarbons like ethane and propane. So it's neither A nor B. Now petrochemicals are actually one of the even lower, so I think you can get those. Getting the petrochemicals seems like a good idea, but petrol is a bit of because petrol is basically just motor fuel, it's just gasoline, so it's a bit of, it's also a fuel. So what would it be? To increase the yield of petroleum or to produce petrochemical? I think B is a good option. So while petrol is less of a used term, it's the same as gasoline, so the answer is both A and B. So I myself skipped this particular topic. I would suggest that this one be really gone over in some amount of detail, because while it's not exactly cracking, it is a part of it, it's giving some context. Number one important point is that mineral oil is the same as petroleum. Right, formed by the slow chemical and biochemical decomposition of the remains of organic matter found between sedimentary rock, and it's in the raw form. It is known as crude oil, is a liquid of blackish color. We get various fractions at present, right? And fraction 1 is natural gas, which is like the one that is the lightest, and that is used as a fuel, and petrochemicals basically to drive other chemicals. Then we have petroleum ether used as a solvent, ligroin or naphtha used as a solvent and raw material, and we have gasoline, which is used as a motor fuel, and usually the ones that we crack are kerosene, oil, and gas oil. So kerosene oil and gas oil are the ones that we usually crack to get what we want. Right. So natural gas is the lightest, used as a fuel. You burn it, especially for domestic work. Petrochemical to derive other chemicals. Petroleum ether, and that is from C5H12 to C6H14. That is used as a solvent, whereas natural gas is from CH4 to C4H10. Petroleum ether is C5H12 to C6H14. Ligroin or naphtha is from C6H14 to C7H16, and gasoline is from C4H10 to C13H28, but mostly it's C6H14 to C8H18. So if you take a look at this, it would be a good idea. So which of the following is the correct name of alkane? 1, 2, 3, 4, 5, 6, 7. This is the big one. 7 means heptane. 1, 2, third. Substituent is on third carbon. So this should be 3-methyl heptane. So which is a ketone? Obviously this one. Which of the following shows functional group isomerism? It's when they have different functional groups. CH3NH, C3H7, and if you, it's 3, 4, 10. Now you have to realize that it's not functional group isomerism if they have the same functional group. Over here, this is actually chain isomerism. This might be considered as metamerism. This may be, chain isomerism. As for this one, 1, 2, 3, 1, 2, 3, C3H6, 2, 6. This is, one is aldehyde, the other is ketone. Definitely what you would consider functional group isomerism. Let's, just to be careful, let's look at this one. It's literally the same molecule, except there has been a change in position. Initially it was between first and second carbon, now it's between second and third carbon, so it's position isomerism and not functional group isomerism. There is a distinction. So now they're asking about the functional group of acid amide, and this is it. This is for acid halide. This is cyano or a nitrile functional group, and just that is for amine. So which of the following intermediate has the complete octet? Methyl free radical doesn't have it because it's 1 electron less. Carboniamine is actually lacking in 2 electrons. Carbene is something I'm not really familiar with, but carbanion contains both of the ones that it wants, so this one has it. This I'm going to check what carbene is. Select from the following which one is an alcohol. This is obviously a carboxylic acid. This one is alcohol. This one is an ether. So obviously the answer is this one. Which of the following is not a type of structural isomerism? Chain is. Metamerism is. Functional group isomerism is. Cis trans is a stereoisomerism, is an example of stereoisomerism. So in which mechanism are free radicals not involved? Polymerization of styrene, they are involved. Halogenation of alkanes involved. What about the cracking of alkanes? I doubt there is any involvement of the free radical mechanism. And then they're talking about the hydration of the alkyne molecule. We haven't done this, but we have done this cracking process, and they haven't mentioned any free radicals, so I would go with this one. So which of the following statements is incorrect about nucleophile? A nucleophile is rich in electrons, that is actually correct. Molecules having lone pair on the central atom, also correct. Oftentimes negatively charged, yes, but not always. Deficient in electrons, nope. This is the answer, this is the incorrect statement. In benzene, the total number of sigma bonds and the total number of pi electrons. Sigma bonds, 1, 2, 3, 4, 5, 6. We have 6 sigma bonds over here. and 6 over here. So in total we have 12 sigma bonds. And we have how many pi bonds? We have 3 of those. In each pi bond there are 2 electrons, so we have 6 pi electrons and 12 sigma bonds. Xylene has how many isomers? We have just done this. It has 3 isomers. Now another important thing about benzene is that it has certain properties that we investigated in different manners, such as its empirical formula was found prior to us having decided what its actual formula is. Now this is some important piece of info. And so you'll have to look at the aromatic hydrocarbon topic, which is page 169. And over there they have written that the empirical formula of benzene was determined by elemental analysis. So they used elemental analysis to figure out the empirical formula, that the empirical formula was CH, and all of these were done prior to us having actually known what the formula or the arrangement was. Elemental analysis. We were also able to figure out what the molecular mass was, and that was done using the vapor density method. And what was it? It was 78.108. Try to remember the exact value in case they will ask. 78.108. And using the empirical formula and the molecular mass, they were able to deduce what the molecular formula was. And when they figured out the molecular formula, what was their conclusion? Well, they deduced that the benzene molecule is highly unsaturated. We need to select a nucleophile from the following examples. This is an electrophile. This is indeed a nucleophile. This over here is an electrophile. I'm not sure what to call this. It doesn't have any available lone pairs, but it's not exactly deficient either. But because of the plus charge, I think it's a lost cause, because it's already given its electrons to a hydrogen, so it's not really an option, so to speak. Right, in 1,3-butadiene, the number of sigma bonds and the pi bonds, you need to draw the structure. Buta means 4, diene means that there are 2 double bonds, and 1,3 shows the position. So 1 over here and 1 over here. So how many sigma bonds and how many pi bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 sigma bonds, and how many pi bonds? 1 and 2. We have 2 pi bonds, we have 9 sigma bonds. And if you are a bit unsure about this, think about it. If this was an alkene, how many hydrogens would we have? And this is disturbing because this means we have messed up at some point. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a bit crazy because I would think that there was one more because of the fact that there's 12. This is just becoming 11. So it's butadiene, 4 carbons, 2 of these, 1, 2, 3, 4, this is good, 1, 2, 3, 4, this is good, 1, 2, 3, 4, this is good, 1, 2, 3, 4. Maybe I'm just being paranoid at this point. Anyways, 1, 2, 3, 4, 5, 6. 6, because 12 -4, it ought to be 8, to be honest. H2 minus 2, and it should have been just 2n, so it should have been C4H10, 1, 2, 10 minus 2, 8, 1, it should be 2n minus 2, so it should be 8 minus 2, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, and one of this and one of this. I'm alright. This is alright. It's 9 single bonds and 2 pi bonds. So the type of structural isomerism, it arises due to shifting of protons from one atom to the other atom in the same molecule is called, and the name is Tautomerism. If we consider the following structure, what is the correct name? We have 1, 2, 3, 4, 5 carbons. We have 2 double bonds at the edges. So the parent name is going to be pentadiene, and 1, 2, 3, 4, and it's going to be 1,4-pentadiene. Easy peasy. Photochemical reactions of the alkene with halogen show which of the following mechanism of reaction? It's obviously free radical substitution. It cannot be anything else. You need to consider the following structure: the carboxylic acid. What is the correct name? We start from this: 1, 2, 3, 4, 5. So it's going to be pentanoic acid. This one is not possible. Naming should start from over here: 1, 2, 3, 4. So it's 4-amino pentoic acid, and this is the name given to an amine when being a subsidiary group. So which of the following is a heterocyclic compound? It's one which contains within the ring something that is not a carbon. Aniline has NH2 attachment that is not part of the ring, so it's not a heterocyclic compound. Styrene is this monomer, C6H5, but again it's not really part of the ring, is it? But pyridine is like this. It's basically just a benzene part, but instead of there being, a benzene over here, there's a nitrogen. So that is what pyridine looks like. And if you want to see this, you're going to have to go to the benzene topic. And just at the start, my apologies, that would be in the organic compounds topic. And just at the start, you would observe on page number 126, they have given the structure of pyridine. The type of compounds which contain an open chain of carbon atoms are called aliphatic, aromatic. No. What does alicyclic mean? Alicyclic are basically the ones that have a ring structure. The name is a bit misleading. We get confused as to what ali part of it means, but it's clearly mentioned in the book. That alicyclic is not what we think it is, because the homocyclic compounds are further classified as either alicyclic or aromatic, and alicyclic compounds are the ones that are non-benzene. And because they're saying an open chain of carbon atoms, it cannot be alicyclic, it cannot be heterocyclic, because heterocyclic has a different distribution. It's distributed into saturated and unsaturated. So you should be really careful about what alicyclic means. The answer can only be aliphatic. alicyclic are homocyclic non-aromatic. Because they may ask you if something is an alicyclic compound, and if you don't know that it needs to be both homocyclic as well as non-aromatic, you're gonna mess up. So these are distribution of homocyclic. So homocyclic can be divided into alicyclic and aromatic, and the unsaturated ones is basically a division of homocyclic into heterocyclic into saturated and unsaturated, and the unsaturated is further divided into aromatic and non-aromatic, because we always have the benzene like portion involved. So if you talk about heterocyclic compounds, the compounds in which the ring consists of atoms of more than one kind, they're called heterocyclic, right? So we have pyridine, and you might consider, and you have to realize that all of the heterocyclic compounds are given. You can divide these heterocyclic into saturated and unsaturated, and the unsaturated can be further divided into aromatic and non-aromatic. And all of the examples that they have given of heterocyclic in the compound, they've given 4 of these: pyridine, furan, pyrrole, and thiophene. They're all from the unsaturated variety. None of the saturated examples have been given. So this is an important thing to get an idea of, to get an understanding of. And this classification is important. It starts from page number 123, and if you read over this carefully, it's written: there are millions of organic compounds, practically impossible to study each individually, so we classify them into various groups and subgroups. And we have a basic broad classification: open chain or acyclic, closed chain or cyclic. We talk about open chain or acyclic compounds. They contain an open chain. The chain may be branched or straight, and they're also called aliphatic compounds, which was a question they asked. Straight chain, the carbon atoms are connected in series. Branched, carbon atoms are attached on the sides. Then there are the closed chains, and these contain rings of atoms known as cyclic or ring compounds. We have homocyclic, also known as carbocyclic, and heterocyclic compounds. And the classification is given: cyclic, further divided into homocyclic and heterocyclic. Homocyclic is divided into alicyclic or aromatic, meaning homo means they all need to be to have carbon, no other. Alicyclic is whether it's in an aromatic formation or in a non-aromatic formation. And heterocyclic, saturated, unsaturated, and saturated into whether it's aromatic or non-aromatic. For heterocyclic, we don't use this particular term of being called alicyclic or non-aromatic. This is something you need to remember, because this is again something we have not done. So which formula represents a compound which has cis-trans isomerism? Well, for there to be cis-trans isomerism, there needs to be a double bond, and over here the fact that we just have 4 attachments is representative of this fact, so it's probably this one. Even if these were somehow attached, even then it's unlikely to be cis-trans. So which is the following is a formula of an alkyl radical. Radical bit is important. So radical usually has one less hydrogen than it can. See an H twin, possibly. See, this is an example of a radical. C1, H twin, it should be 2n plus 1. Because if it's an ethyl radical, it's C2, H5. So this is the formula that suits. So the correct order of priority in case of polyfunctional group is, and polyfunctional means it should contain more than one. So carboxylic acid followed by aldehyde followed by ketone followed by acidamide. Probably aldehyde, ketone, this is wrong. Carboxylic acid has the highest priority. Again wrong. This is a bit iffy. And acidamide is basically like this, right? I don't think it has greater priority, so to speak. But let's see if it's written anywhere in the book. Let's go to the carboxylic acid topic. The naming of the carboxylic acids is definitely included, so it might be somewhere over there. So in the introduction, they haven't said much. In terms of naming, maybe the imide portion is somewhere. In the formation of imide, they've just literally given the mechanism. Do you know the formula for how an imide is made? Initially we get an ammonium ion, and after the ammonium ion has been decomposed, we get the amide. I honestly doubt if there is any priority, so to speak, of. Carboxylic acids tend to have the greatest priority there is. As the number of carbon atoms in the homologous series of alkene increases, for which property does the numerical value decrease? Density, number of isomers, wrong. Enthalpy change of vaporization, maybe. Vapor pressure. The vapor pressure actually increases because, no, it should decrease because the intermolecular forces are increasing. At any temperature, the vapor pressure should be less. So this is option. Enthalpy change of vaporization should increase, and so should the density. But the vapor pressure ought to decrease because the values of the intermolecular forces are increasing. Again, good idea to look at the alkanes topic, see if there's anything in the physical properties. Alkanes or the paraffins. Right. Number 1, alkanes containing up to 4 carbon atoms are colorless and odorless gases. Right, and if you compare to alkenes, it's up till C3 that they're gases, and from C4 to C15 I think they're liquids, while from peptane to heptadecane they are liquids. So for alkanes, C1 to C4, colorless and odorless gases, and from C5 to C17 they are colorless and odorless liquids, and the other are waxes, which have the same property of being colorless and odorless. So these are physical properties you should remember. Now the thing with alkenes is that they're different from alkanes in that they have a characteristic smell. And this is an important difference. And the alkenes are gases from C1 to C3 and liquids from C5 to C15. So alkanes are non-polar or very weakly polar, whereas the alkenes are, somewhat or weakly polar. They do have some amount of polarity and are insoluble in polar solvents like water, but soluble in non-polar ones. The physical constants like boiling point, the melting point, and density increase with the increase in the number of carbon atoms, whereas solubility decreases with the increase in the molecular mass. So important that density increases as the number of carbon increase. The boiling point increases by 20 to 30 for each further addition of CH2 group. So per CH2, BP increases by 20 degree to 30 degree. And the boiling point of alkanes having branched chain structures are lower than the isomeric normal chains. N-butane has a higher boiling point than isobutane. And the melting points of the alkanes also increase with the increase in molecular mass, but the increase is not regular. And the changes in melting points are very seldom regular. You would observe this trend. So if we compare these properties with that of carboxylic acids, yes, the melting points of the carboxylic acids increase irregularly. Irregular increase in MP and N-butane and isobutane. So points to remember. Now if you look at the next part of it, there is combustion, and complete combustion yields CO2, H2 and heat, and the amount of heat evolved when 1 mole is burned is the heat of combustion. And you should know that the heat of combustion of CH4 is given, and it's given as 891. Good idea to remember that. The reaction is highly exothermic but requires high temperatures to start. So that is important. Now let's move onwards. And the total number of sigma bonds between CH6, in which the following class of organic compounds, the position of the functional groups is not indicated while writing the name according to IUPAC. It is indicated, because carboxylic acid is literally always at the end. Organic compounds show all of the following properties except catenation is this ability to have like so many like see carbon on carbon on carbon on carbon. Resonance as shown by a lot of compounds, and isomerism. The isomorphism is something that is shown by crystalline structures, in inorganic crystalline structures in general. So what is the number of isomers of C2H to Cl2 including cis trans? Well, if it's like this, we can have one of these. We can have one of these, we can have the two isomers. So we have 3. Let's wonder if there's a fourth way of this. Now we have done the cis trans. Is there any chance of optical? There isn't. Chain, definitely not. Position isomerism, yes, if we put on the same side or on different side. What about functional group isomerism? Unlikely. Answer should be 3. Which of the following aromatic compounds contain 2 benzene rings? Xylene, no. Naphthalene, yes. Toluene, no. Anthracene contains 3. Which one of the following compounds does not show position isomerism? Dichlorobenzene ought to show. Propanol can show. Butene can also show. Propene cannot show because wherever it is located, the molecule will still remain the same. So butan 2 all and butan 1 all show which of the following types of structural isomerism? Metamerism, no. Position isomerism, yes. Can't be because the function group is the same, the chain structure has not been changed. Which show tautomerism? Alpha amino acid, yes. Vinyl alcohol means on the same. Vinyl alcohol would suggest that it's like this. Or A and B. Ethanol is unlikely. I'm going to have to research what vinyl alcohol is. There is vicinal that are on the same side. There is geminal which is on the same side. And vicinal means on the same carbon. What does vinyl mean? But the fact is that tautomerism is shown only by amino acids or by ketoenol groups. And these are neither. So the answer is A. The consecutive members of a class of organic compounds which differ by CH2 are called homologues. Homologous series is referring to the series. Homologues are referring to the individual members. So hopefully this was helpful. If